Okay, hello everyone. Thank you for being at the ESIC seminar today. Our speaker today is Dr. Cui from Oklahoma State University. He'll be speaking to us about composable, expressive, and portable modeling for high-performance power system simulation. Dr. Cui is an assistant professor with the School of Electrical and Computer Engineering at Oklahoma State University. He was a research assistant professor with Current and the Department of EECS at the University of Tennessee, Knoxville, where he received his PhD in 2018. He is the author of ND is an open source tool for power systems modeling and analysis, and was the chief technologist of the Current large-scale testbed, which won 2020 R&D 100 awards. His research interests include computing, software engineering, dynamic performance, and cybersecurity of energy systems. Thank you, Dr. Cui, for being with us today. Back to you for the presentation.
Thanks, Anamika, for the introduction, and thanks to everyone for attending this talk. So today I'll talk about the design and implementation of a framework for power system simulation. So overall, this is the outline of the talk. So I'll introduce first how models and transient stability simulation is represented in computer programs. And then I'll talk about the design of a descriptive modeling framework that are expressive and composable for constructing those complex differential algebraic equation-based models. It has the ability to generate code so that the user can be absolved from writing very complex programs. And then we will talk about some design considerations to achieve high numerical efficiency and show a Python-based example. And that will be extended to high-performance solvers and high-performance hardware in the Julia programming language. And in the end, I'll provide an outlook for heterogeneous computing through code generation. So first of all, I want to thank the support from DOE and SF, and from Current, and from Oklahoma State University. And in particular, I want to thank the graduate students. Jinying is with Dr. Friendly at Tennessee, and two of my graduate students who have contributed to the development of this project. So the background for the talk is transient stability. A lot of you may have seen this power system timescale picture here. So power system events spans from microseconds to milliseconds and then to seconds. In the time frame of millisecond to a few seconds, there is one region that we call it electromechanical transient timescale. So this is driven by the rotating mechanics and the control in the electrical part. And stretching it to the longer time scale, we have the extended term time scale, but these all fall into the power system transient stability time frame. So formally, power system transient stability is defined as the ability of a generator or a group of generators to remain in synchronism immediately following a severe and sudden disturbance. We know that there are two major categories of methods to study power system transient stability. One is through analytical methods, such as energy function methods, or in general, Lyapunov-based methods. The other major category is numerical simulation, that is using computer models to run a lot of time domain simulations. So they're also known as transient stability simulation. Transient stability simulation is very widely used in the industry for transmission planning to ensure compliance with NERC standards. And today, this talk will mostly focus on the modeling and simulation for transient stability simulation. So mathematically, transient stability simulation is an integration of the so-called differential algebraic equation, where the first equation, x dot equals f, is a differential equation, and the second part, this is an implicit form of an algebra equation. The simulation is usually given at a steady state, which when t equals 0, this differential equation will become 0, and the algebraic equation will be 0 as well. That's known as a steady state. At a particular time of interest, TD, where disturbance happens, we can change some conditions to the DAE system and cause some mismatches in either the algebraic or the differential equation. For example, we can change the load or generator at a particular time to a new value. So this creates a disturbance, and by running this integration, we can solve the trajectory for transient stability. There are two major steps at each time step. That is to calculate the residuals for the F and the G equation for the whole system, and then solve this DAE. So the second part can be implemented by standard solution methods, such as trapezoidal methods or Adam-Bashforth methods that have been discussed widely in textbooks. So we will talk about how to formulate the residual equations F and G for the whole system. So for the whole system, it's not calculated all at once because a complex power system is composed of many different generator, controller, and renewable models, for example. So it is in fact obtained by evaluating each device, each generator device, each controller device, for example, and assembling the results to form the residual equation for the whole system. If we consider a 3-bus system, we have 2 arrays. The first array is for the residual of F, and the second array is for that of G. Suppose that we have a network, right? Then after evaluating each of the line devices or using the Y bus, we can obtain the injections into the network, and that becomes part of the power balancing equation. Next, on the first bus, we have a generator. So after evaluating that generator, we have the differential for the speed and angle. And we also have the boundary variables. These are the power injections into the network. So the second bus, for example, has a wind turbine and converters. So after evaluating this device, we can obtain those differential variable derivatives as well as the power injections. The last one has a load. So it might be a motor load, so we can introduce one differential variable along with the network power injections. So our goal here is to build this residual equations for the whole system. As we can see in this process, it involves a lot of those models, and in a typical industry simulator, there are several hundreds of models. And most of those modeling efforts are made to deduce and implement equations for various models. For example, those renewable models are highly complex to calculate the derivatives and figuring out the power injections into the network. So previously, to develop a model for research, one can first program the residual equations in the scripting environment and code solvers. A lot of us have done those in courses by implementing a, say, single machine infinite bus system, but this can be error prone, and this is not readily scalable to large systems. The other approach is to program the model in a commercial simulator framework, but this is more challenging because it requires specialized skills for the specific framework. One has to know where to put those equations in that framework. And in addition, it typically requires proficiency in system programming languages, and that can include Delphi, C++, or Fortran. And for those industry-grade models that has more complexity, so research are being hindered because implementing those models alone is very programming intense. So complexity in the implementation involves the combination of high order transfer functions, discontinuities such as limiters and deadbands, or irregular blocks such as delays, state freeze, conditional hold. Some of those may be familiar to if you have looked at those industry renewable models. So when a voltage dip comes, a state needs to be frozen and remain frozen after a designated seconds after voltage recovery. So these are difficult to implement and troubleshoot. And moreover, there is another issue that is sometimes neglected, that is limited portability between simulation frameworks. For example, if I have implemented the model in MATLAB and I want to migrate it to PSSC, for example, then a lot of times it requires a major effort to rewrite it to a new framework. The fact is that the computation techniques are evolving very rapidly, such as we have GPUs with a lot more power. But to utilize those power, we have to develop new software framework, which may include a new organization of data and the way we do computation. And when new framework emerges, limited portability will require major implementation efforts again to adopt those models. This is an example of the complexity in model development. Here we show an IEEEST stabilizer model. So the code here is just a snippet from my previous implementation in Python here. We can see from this model block that there are two lead left blocks that are pretty much the same, but with different inputs and different parameters. And as a result, in the code, we have duplicate code here in the differential and in the algebra equations. So these can be unfavored in terms of maintenance. And moreover, to utilize an implicit integration framework, one needs to manually derive and program the partial derivatives, which is again trivial and error prone. So how to simplify this complexity? So our motivation here is to develop a software framework to enable rapid prototyping of sophisticated models for research. And we want to support portability between various simulation environments. And moreover, we want to achieve high computational performance on heterogeneous computing architectures that are emerging now. So put it in short, we want to develop more models just for once and reuse them in different ways. We start from a few observations. So first of all, that is modularity in the dynamic models or in the transient models. So this is again an IEEEST stabilizer model. We can see that all dynamic models contain the same categories of elements. They are parameters, variables, equations, and discontinuities. For example, this is a hard limiter here. And many controller models are composed of a limited set of building blocks. So these transfer functions are the building blocks that appear very often. So the first objective here is to allow descriptive modeling by using equations and the building blocks instead of requiring any specific implementation. We want to look at this model and describe how these transfer functions are connected. The second observation is that equations represent relationships, not necessarily how they should be implemented in computer code. So for example, models in the DQ axis usually convert terminal voltage to an internal reference frame by using VD equals something like this and DQ by doing the DQ conversion. So there is a trade-off between readability and computational efficiency. If we introduce VD and VQ as two algebraic variables in the model, we will greatly increase the number of variables in the DA system. And a lot of you know that LU factorization scales to the cubic of the number of matrix dimension, and this can create some computational complexity. But again, this expression is readable. So there's a trade-off between writing the code that is readable to the developer and making it run fast. So our second objective is to leverage computer algebra to process model descriptions and generate optimized symbolic representations. We want the developers to write models in an expressive way, but internally will be converted to a computationally efficient way. So the From model descriptions to simulations, there is a gap. If we have developed the models already, it won't be simulatable yet. So those model representations need to be generated into numerical code for the ultimate simulation. And there are some design decisions on data structures and computational workflows that will determine how the code should be generated, or say how the computer should write the code. So the objective 3 is to design data structure and workflows to reduce the complexity of generated code, and as a result, improve numerical efficiency. So we propose a layered architecture for modeling and simulation. So the idea is that the user prepare descriptions for those models, such as generators, controllers, and etc. Under the hood, the architecture, the framework will perform computer algebra-based symbolic processing by converting those descriptions into implementation-agnostic symbolic representation. We apply equation optimizers so that we have a reduced number of variables in representation. By calling proper code generators, we can convert those symbolic representations into target code that are run for numerical simulation. Those target code can be coupled with a simulation framework that is efficient. So there are a few advantages here. First, we have a clear separation between the model description and the actual implementation. So the modeling user only needs to care about how to describe a model. So all equations described by the user will be optimized, but to the user, the description is still readable. So looking at those symbolic representation, we can reuse those optimized representations for different simulation frameworks by swapping in the desired code generator. So the idea here is analogous to a compiler for computer programs. So this is a highly simplified architecture of a compiler. Compiler take high-level code, which could be C, Julia, or Rust, converts that into an intermediate representation, and then generate object code for the target hardware. Likewise, we take in model descriptions and generate code for the simulation framework. So to implement this framework, we start from the abstractions for power system models. We observe that power system models are consist of parameters, variables, equations, and discontinuities. So as an example, we describe a shunt device model, which injects active power and reactive power based on susceptance and conductance. So this is a Python code snippet for describing a shunt. So first, a shunt is connected to a bus. It has conductance and susceptance, which are given from the data file. And the shunt connects to a bus and retrieves the angle and the voltage variables from the bus by accessing the bus variables using the bus indices. Recall that the phase angle corresponds to power balancing equation. So to that corresponding equation, the shunt injects the desired amount of active and reactive power. So this can be seen as a domain-specific language for describing a power system model. The next challenge is about discontinuity. So there are a lot of discontinuous models in a practical model, and they're very common. So in our implementation, a discontinuity block basically exports flags that can be used for constructing piecewise equations. For example, this is a hard limiter. It takes in one variable, checks whether it's within the bound or not, and exports 3 flags. So 3 flags to indicate whether it's pegged at the upper limit, or it's at the lower limit, or if it's within the bound. So by using these 3 flags, we can construct piecewise equations for this hard limiter. So as an example, a power system stabilizer usually have an output limiter to check whether the voltage is within the limit. If the voltage is within the limit, stabilizer output will be provided. But if the system has some under voltage or over voltage issues, the stabilizer will be disabled. So we create a hardware limiter called OL, output limiter. It basically takes in the terminal voltage as an input, checks against the upper limit and lower limit. So it exports one flag called _ZI to indicate whether if it's within the limit. So if it's within the limit, so V out will be equal to VSS. Otherwise, V out will be 0. With the equations and the discontinuities in place, the next step is to think about further simplification. And we come up with modeling blocks by observing the repetitive occurrence of transfer functions. So we want to describe models using blocks instead of individual equations because they can reduce duplication and improve readability and maintainability. This shows a low-pass filter, which takes an input and gives an output. This is the differential equation for it. If you want to write this equation out, it'll look like this. This is a variable name. We have a state, which is, this is the right-hand side of the differential equation. So this is not ideal. We want to instead write it like this. So self.lag equals a lag, and the input is self.u, time constant is self.t, and the gain could be 1, right? The bottom is more readable than this upper one. So we provide those bundled equations and discontinuities. Basically, under the hood, the lag class shown here defines a state with equation templates, because by the time we define this lag class, we don't know how it's going to be used, but we know what the equation looks like. So internally, it has a state, and the equation will contain those name templates where, for example, K's name, U's name, and its own name remains to be defined upon instantiation. So when someone instantiates this lag as an LG block, so we can perform namespace substitution by taking the name from here and putting it to self.name. The U's name is here, T's name is T, K's name is 1. So after plugging those into this template equation, this state, now with the correct equations, can be exported to the model. And this can scale. We can utilize these to implement those much more complex models, and this lag is just one example for illustration. So with those techniques, again, this is the IEEE stabilizer example, but now the implementation is a lot more simplified. There's just barely over 20 lines of code to implement the equations for them. So first, we just look at the model here. We have two high-order filters. They're imported from the model, and we just describe the model by declaring F1 as a lag second order, plugging in the input, the parameters, and then provide F1's output, which by convention is named F1_y into the second block. And by following this description, we basically implement the whole model. So this is overall intuitive and maintainable. And think of it as a coding-based Simulink with vectorization, which will be discussed in a bit. So the introduction of blocks solves the maintainability complexity. So here we have much more maintainable complexity in the models. So here models use those available blocks, discontinuous blocks, and services, which can be utilized to implement any arbitrary computation. So now the key is that maintenance efforts now scale to the number of building blocks, not that of the models. Even if we have hundreds of models, they still utilize the dozens of building blocks. And each building block encapsulates very few equations. These can be easily maintained. So we provide a lot of blocks like lag, lead lag, washout, gain, integrators with respective anti-windup variants. This, like for the discontinuous blocks, we have hard limiter, anti-windup limiter, deadband rate limiter, etc. And we also have services, which, if you're interested, they are used to implement any arbitrary irregular calculations, such as flagging a low voltage event or holding a variable for a number of seconds, and etc. So overall, the maintenance complexity has been significantly reduced. So using those model building blocks to develop models, we have developed nearly 100 models that include generators, exciters, turbine governors, stabilizers, etc. This is just a screenshot of the names of the models we have implemented. So from the model description to the symbolic representation and simplification, we utilize the computer algebra tool and symbolic, which is also known as symbolic tool. So the symbols for the variables and the equations can be extracted from the model descriptions, as we have seen. This block here shows the equations that describe the classical generators. So we have included all the algebraic variables for readability. But in fact, they can be optimized by eliminating algebraic variables in partial or in full. So the idea is to solve for PE and QE, since we have assumed the power injection model, as a function of parameters, network variables, and differential variables. So this is the result of simplifying this model by applying this computer algebra. So this one next is a recording showing this simplification in action. So we extract the algebraic variables and algebraic equations for gen class, and now call the solve function to solve for all the algebraic variables. Now we show the result for PE and QE, and at the same time, we can obtain the solutions for all algebraic variables. And lastly, we can use the symbolic tool to call the Jacobian function to calculate the Jacobian partial derivative elements. So this is overall efficient because this all happened in the back of scene and only needs to be done for once. So from the symbolic representation to simulatable code, we need to discuss code generation and the simulation framework. Note that these two are tightly coupled, and we need to make design choices in terms of the data structure and the formulation of DAE to ensure efficiency. So first, we discuss how we organize the data for simulation. So this is a design decision called vector for data vectorization. Excuse me. So the first very common type of data structure is called array of structs. Basically, this bar here is one array, and each element here is one structure for an individual Gen class device. So we have those Gen class devices next to each other, and inside each device, we store their parameters, their variables, their derivatives, and so on. So the code would be written in a way that enumerates those devices, retrieves the parameters and variables for each of them, and calculate the equation residuals. But this memory layout has one major issue. So processors grab data from the memory in chunk. It doesn't grab it in an interlaced manner. So here, if the computer prefetches data in this block, but if those data are not immediately used in this current computation, it'll create so-called cache misses. And also, this for loop may involve some conditions, if conditions, that'll prevent the compiler to vectorize this code on hardware. The alternative approach is called structive arrays. So this is just one structure. And this structure demonstrated here has 4 arrays. Each of them store the whole array of the rotor angle variable of all the gen class devices. So in other words, they're stored in contiguous memories. So when we retrieve the data, we retrieve all the delta, all the omega in once, and call the calculation in once, and put those all vectorized data into the new array. So there are fewer cache misses because all the retrieved delta variables will be used during this calculation. And this naturally supports single instruction multiple data because the processor can retrieve a number of 8 data in the same time and do the calculation using those specialized instructions. So this is our choice for the data structure. And there's another issue with the time constant, which is because it is a convention to use models that has 0 time constant to create pass-through blocks. So in this block, if one sets t to 0, this should become a pure gain block. But in computer implementation, when one has a 0 here, it'll create a division by 0 issue. So one solution in commercial software is to introduce an if-else condition, but it unnecessarily complicates the code generation and creates difficulty for compiler optimization. So we want to seek a unified formulation for models with 0 and non-zero time constant. So the idea is to reformulate the DAE a little bit. So it was x dot equals f. Now it becomes m times x dot equals f hat. As long as a condition is satisfied, those two formulations are equivalent. But here you can see there is no division by 0 problem if all the denominators are moved to the M matrix. There are different ways to choose f hat. The first simplest choice is to move around the denominator. Just move the t to the left-hand side, and it becomes t times y dot equals the right-hand side. This is simple yet effective because it can be done programmatically. But we also note there is a manual reformulation technique by exploring the specific structure in the model. So this is a subtransient synchronous generator model where we can see we simply move those denominators to the left-hand side. But following some equations in the book, we can see that the right-hand side actually contains the derivatives of others. So we can introduce another time constant and move another derivative variable to the left-hand side. But this has to be done on a case-by-case basis. So with the code generation in place, we can generate Python code which looks like this. This is the residual for f, and this is the residual for the algebraic equations. By swapping in a Julia code generator, we can write code for Julia. This is my favorite because we see clear separation between retrieving variables, expanding the equation right-hand side, and calling the kernel calculation functions. We can also swap in a LaTeX generator because they are basically symbolic expressions and they can be turned into LaTeX strings. So all those equations you will see in the Andy's manual are generated automatically. So the takeaway is that one only needs to call and implement a code generator to adapt to a different language or hardware. So suppose that we have generated Python code, and to make it simulate, we need to organize the system, organize those functions for individual models into that for a whole system. That's done by a so-called call orchestrator. So they will evaluate the discontinuous blocks, evaluate the residual equations, evaluate the non-wind-up limiters, and then build the whole system residual array for the solver. So this is kind of implementation heavy, but if you're interested, please refer to the code base. So to make it simulate, we need to provide the input data for the cases and call the solvers. And we make one design decision by using implicit DAE solvers because first, they're numerically stable, and second, they don't involve the they don't involve the manipulation of the Y matrix. So the other benefit is that we can utilize sophisticated DA solvers from the scientific computing community. So this slide shows the accuracy verification of this framework implemented in Andes for IEEE 14 bus system. We used a variety of models for the demonstration, and we compared the result with DSATools TSAT. So those solid lines are from Andes and dashed lines are from TSAT. So you can see perfect match between the Andes and TSAT results for different variables. For a larger system with a number of models, we also see exact match. So this has verified the accuracy of the proposed modeling and numerical simulation framework. So summary for this part is that we have a composable and expressive modeling framework to implement complex models for transient stability simulation. We have a separate descriptions from the actual implementation so that optimizations can be performed using computer algebra tools. Code generation can convert the model descriptions into different implementations. We have seen the Python-based implementation, and we talk about design decisions to achieve high computational efficiency and convenience. So next part, we'll show some research using this framework. So the first one that came to my attention is the availability of many DA solvers in the Julia scientific computing community. So there are a number of solvers named here, but they're implemented in a different language. Can we wrap those models generated for Python and interface them with the sophisticated DA integrators? If that's possible, then we will have access to advanced features such as automatic order selection and step size or error control available. So I did that programming. So our symbolic numeric framework, as we discussed, works with all the DA solvers in Julia. And all I needed to implement is a thin wrapper, which is around 200 lines of code. So the plots here show the performance of the 4 different families of solvers. So the error here is smaller on the left-hand side, and as a result, to achieve smaller error, the computational time is usually larger. So first we look at the trapezoidal method, which is in the upper right. So the blue line here shows the performance of the trapezoidal method, which is quite decent because we have a good trade-off between time and accuracy. But at the same time, the high-order Rosenbrock method here shown here, for example, this point, can achieve a higher accuracy, which is 10 to the negative 5, and with a shorter computation time, which is below 0.8, as opposed to almost 0.9 in the trapezoidal method. So this is also performed in an UK 2000 bus system, and the pattern is similar. And again, the trapezoidal method is pretty decent. But the significance is that one can benchmark and select solvers to meet speed and accuracy requirements. And more importantly, this separation of models and solvers allow power system software to utilize the advancement in general scientific computing. So after experiencing the power of the Julia language, so there are another observation, so that is the residual calculations in Python are not fast enough. We have seen that the time here are pretty much in the same order of magnitude. Is it because most of the time are spent in Python to evaluate those equations, and they're not fast enough. Julia, on the other hand, is just in time compiled to machine code and can leverage multi-threading and single instruction multiple data vectorization on processors. So can we swap out the Python code generator and swap in a Julia-based code generator so that all the code base is in Julia, can be compiled and achieve high efficiency? So I did a proof of concept study. Instead of doing a full transient stability simulation, I attempted a parallel power flow calculation in Julia. So we want to see the performance improvement for vectorizing those calculations on CPUs in the Julia language. PowerFlow, on the other hand, only solves the power mismatch equations. So there are 4 steps in the Newton method for PowerFlow calculation. We need to calculate the residual equations, update the Jacobian matrix, call the nonlinear solver to solve for the increments, and then check for convergence. And we focus on, again, the building of the residual and the Jacobian elements. So we propose 2 parallel workflows. One is called inter-model parallelism, and the other one is called intra-model parallelism. So from the name, we can tell that inter-model parallelism basically creates parallelism across the models. A typical serial call basically evaluates the power injections for PQ, PV, slack bus, line, and shunt models separately in serial. But an inter-model parallelism calls them in parallel, for example, by using multi-threading. The inter-model parallelism here aims to parallelize the equations within an individual model. For example, the PQ model has 2 trivial equations to impose P and Q. So previously they were run in serial, but the inter-model parallelism aims to run them in parallel. We can combine the 2 to create a so-called nested parallelism, which parallelizes across the models and again parallelizes across those different equations. So the implementation for inter-model parallelism is based on multi-threading because we can use one CPU thread to run the calculation for one model. Intra-model parallelism can be done by multi-threading again, because we can use one thread to calculate one equation in each model, or we can use single instruction multiple data to parallelize the individual calculations within a model. So as an example, so we calculate the injections from lines by using the line equation. This is the expanded polar form of line injection from the sending end and the receiving end. Intermodal parallelism basically parallelizes the line with shunt, but intramodal parallelism aims to parallelize the calculation of P at the sending end with the calculation of P at the receiving end. If we do it in single instruction multiple data, so what it does is to calculate the vector of VH squared in parallel. That is, we take 8 elements in this array and do that calculation in just one CPU instruction. So SIMD here can be verified by inspecting the assembly code generated from the Julia code. So here, these are the assembly code, and we can see the vmul-pd, which means vectorized multiplication of packed double precision data. So if this is caught in the generated assembly code, this indicates that we have achieved SIMD. So we benchmarked this parallel power flow calculation in the synthetic 70,000 bus system because we need a large system to show the performance gain. So in this table, we divided the intramodel parallelism approaches from the intermodel parallelism. So a traditional serial calculation achieves equation evaluation in 5.5 milliseconds. But if we parallelize those models, we calculate lines in parallel with the shunts, for example, and we can achieve a reduction to 1.2 milliseconds. And the table here shows the time for this individual model. So for multi-threading, it is the slowest thread that determines the overall execution time. And that is verified in these individual calculations because you can see line model takes about 1.2 milliseconds, and that is the exact time for multi-threaded calculation. But if we do SIMD here, this can be reduced to 0.6, even if we're doing it in series, because SIMD allows line calculation time to be reduced to just 0.5 millisecond. So on the other hand, there are another weird situation here. If we apply multi-threading for the model, intermodal and intramodal calculations, we see that the calculation time is even longer than the serial calculation. This is because if we run out of thread, this will effectively become serial execution plus the multi-threading overhead. So my conclusion is that SIMD alone is effective because putting multi-threading on top of SIMD can only reduce the time from 0.6 to 0.5, but it breaks single threadness. We can use multi-threading for multiple cases. In addition, we can use multi-threading for more cases instead of just accelerating that 0.1 millisecond. So we don't want to exhaust stress. This table here compares the computational performance in milliseconds for various systems, and our comparison is met power. Although the underlying implementations are quite different between these two tools, we can see some acceleration from 2.6 to 2.4, and compared with Met Powers, our method is 20% faster. We all know that Met Power is highly optimized, but we are achieving a better performance. So the significance in this work is that we have proven the portability of proposed modeling framework. There is a way to generate code into Julia and leverage the high performance framework in Julia. And this is the proof of a concept to achieve high performance in PowerFlow. And the next step is to achieve high performance for transient stability simulations, which is by nature a lot more complex. In the future, we also want to leverage heterogeneous computing architecture. That is, we want to utilize GPUs at the same time when leveraging the CPUs. So just an outlook for heterogeneous computing, because our ultimate long-term goal is to let simulations scale to the full capability of parallel computing hardware. We are still very far from there because this requires a deep understanding of how data should be organized for the new parallel computing devices and how our calculation workflow needs to be redesigned, and eventually how to rewrite the programs to exploit those power. This has to happen. Otherwise, the simulation speed 30 years from today will still be as fast as we have today. So the conclusions and takeaways are here. We propose a layered architecture for modeling and simulation, which are bridged by code generation. Complex models can be rapidly prototyped for research by the composition of equations and modeling blocks. And model descriptions are implementation agnostic and thus can be generated into various numerical code for portability and performance. We also present a proof of concept study that achieves high performance in PowerFlow calculation in Julia to show the potential of code generation. So this is it, and this is my favorite slide, so I'll stop here, and I would be glad to take questions. And by the way, if you are interested in trying out the Andy simulator, please visit this GitHub repository. We also have a documentation for it.
Yes, thanks, Hunter, for the interesting presentation. Let's thank our presenters. And we'll open it up for questions. So do we have anything from the audience?
We have some.
No?
I have a question. So you're mentioning that there were some challenges for simulating the transient stability. What sort of future work needs to be done for that to work out in your?
So So yeah, in the talk, I mostly talk about the modeling complexity. So here, let me just exit the presentation. So we have solved the complexity issue to develop those industry grade models for research, right? Because we now have composable modeling. But the major challenge there is to utilize the parallel computing devices. For example, GPUs are a lot different than CPUs. They have a lot of threads, but they have limited capacity for doing if else or flow control. We have to restructure the calculation so that the ratio of computation over data fetch is large.
Okay, and then I'm interested in the tool. So if I go on GitHub and I download this, is there sort of a base case that is sort of implemented so that I can run it and see how the different parts work together?
Yes, that is available in the documentation. So
Awesome.
So the website is docs.andys.app. We have, I would say, pretty good documentation for getting you started. So there are commands and code for doing the examples, and we also have examples for you to play with. For example, these are Jupyter Notebook examples. You can download them, set it up, and immediately run on your system, and you will see the results immediately by running those commands.
Awesome, thank you.
Welcome.
So we have a question online. So Hunter, the question is about, can you highlight what are the main differences between your approach and the existing approaches that are used in industry?
Yes. So the I looked into how models should be written in PSSC, in TSAT, and Power World. So they all deal with implementations. That is, the developer directly writes the target code for the desired framework. For example, in one of the software, you have to define an f of x derivative function. You need to implement in C++ how to calculate those equations. But the discussions in this talk is at a higher level. We only want to describe the models without caring about the specific implementation. So we can write one model description and generate code for PSSC, and at the same time generate code for TSAT or Power World or others. But if one had programmed a model in PSSC, there's no way to generate code for TSAT unless we just completely rewrite it. So this is one of the major difference in modeling.
I see. That's actually very interesting. So it basically provides kind of an a tool to hook any kind of solver, any kind of system, any kind of simulator that you want to work with by following that fundamental principles of code design and code generation, and then you go to solve the problem, right?
Exactly. And I would add that this is future proof because the new simulation frameworks will emerge, but we don't want to redevelop the hundreds of models for the new framework. The separation of description from implementation just prepares us for the emerging frameworks.
Right. So let's see if there are other questions online. Sanjeev, you go ahead and unmute yourself. You can ask questions.
Yeah, thank you. It was a great presentation. So I was wondering about the types of scenarios you run through. I mean, the dynamics, the stability you mean. Anyway, you're capturing the fundamental principles or the equations of the each block, starting from the generator. So I saw the way of formulation you did it, but I was still wondering about the converters or the logic wise, as well as the different test scenarios, because I saw the fault and the two test scenarios that you conducted and validated the results. What about the other type of scenarios, or what are the resonance or because that's a typical now, power system resonance that's keep coming in a bulk power system level, and there's harmonic power quality, a lot of other issues. Have you ever tested these things, the same kind of performance is expected out of it?
Yeah, this is a very interesting question. So first, about the converter models, we have implemented the second generation converter models, basically 7 models that include the whole RE series models, including converter model, electrical control, plant control, like pitch control, aerodynamics, etc. So these all have been implemented, and we have developed. We mentioned this briefly, that we have developed the services here to support those irregular functions, such as holding a variable in a converter. Then the second part of the question is to validate these for the transient phenomenon. So I would say, so first we applied the implicit integration method. So it allows us to simulate timescales from milliseconds to a slightly smaller timescale because numerically it is stable. It's not like the explicit method where the time step has to be coordinated with the model to maintain numerical stability. But in terms of validating the phenomenon, we need to first check that if all the models, if each individual model is implemented correctly. And to me, that is an ongoing work because it is very difficult to validate every nit and bit in that converter model. There's a lot of logic in there, and now it's done by hand. But I'm thinking about ways to automate those tests. Just for example, that might like a governor step response test or exciter step response test.
Thanks, Anja. So,
Thank you.
thanks, Ajit. So I have a follow-up question, Anja, and this is maybe we can end at this note. But so there are transient stability simulation definitely are the hardest of the simulations or calculations that we do at the power systems, right? And when we think about scaling it for large system, it's going to be more and more challenging as we have more inverter-based resources. We have more, distributed resources, more sources of these kind of discontinuities added to the system. So your approach to look into this problem is really taking the full advantage of the parallelization and the computer architectures and coding environment itself to solve this problem and scale it up. I would like to hear your thoughts on there is a parallel direction of research where people look into how to simplify the model itself so that we can get similar kinds of result. We're not solving the exact system, but we're solving some sort of approximate system and still work with it. Do you see in future the use of those kind of simplified model within this framework, or do you see a future where we want to do more and more exact simulation by leveraging the computer architecture that we have available? So just some of your thoughts.
Yeah. Thanks for the comment. And that is one comment I get from one of the proposal reviews. And I think these two complement each other. So model reductions can happen offline. That is to construct test cases using dying red, for example, that are simplified, or from this core orchestrator. Now we simulate the system as a whole, but another core orchestrator can partition the system into subsystems and solve them individually, then interface them. So my approach is to leverage the computing power from the computer architecture. And I think that is the foundation for the simplifications that are going on in other branches.
Yeah, the reason I ask this question is because as a power systems researcher, we do not understand how much of the computing resource we have available from the computing side. So if these two could be combined, I think it could be much more powerful in terms of scaling it for larger systems. So
yeah. Thanks.
Thank you
That's good.
for very interesting presentation. And let's thank our speaker once again. And we'll call it an end for today's seminar. Have a wonderful day, everyone. Thank you.
Thank you. Have a nice day.